I got it. I will begin with a word of prayer. Ahem. 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 Thank you. Dear Father, we thank you for this day. I thank you for the students again, Lord, and just pray that you just bless this class today. Help us to prepare for test 3, just to wrap up any remaining questions, Lord. In your name I pray. Amen. So, unless I'm missing something, I don't think I am. We're pretty. I mean, we have seen a lot of examples of most everything that's relevant to test 3, and I think given what we've done and where we are, I think we can afford to take Friday to cover the material after test 3. And part of the reason that I think it would be wise to do that is I have a trip that I'm taking to Arkansas, I forget, like the 23rd or 24th, so I'll be gone like a day or two there. And so just to be on the safe side and make sure we don't rush the tail end of the material past test 3, I think it would be wise just to take Friday to do stuff past test 3. This should not be confusing because it's a totally separate topic. It's like polar coordinates. So I think, in Calculus 1, sometimes you give a test on definition of definition of derivative from the limit. So, if I was to give the lecture ahead where we actually stop using limits and start using power rule, that would be very foolish because then everyone would just use that on the test, right? You guys do anyway because you remember it from high school. But this is not like that. So I think that it shouldn't damage you for test 3. Now, on the other hand, if Friday you just all have so many questions about the material that we're currently on, then I'll forego that plan and take your questions, right? So it's kind of up to you guys. But let me give you the all-important number. Let's see here. Although first I must connect to the internet, apparently. So you guys have any questions while I'm doing this silly stuff? Yep. 112? Let's party like it's 7464. There you go. Did I hear 112? Oh. Ooh, exciting. Ooh, I like this one. So we're looking at dy dx equals to what? Square root of x squared plus 4x plus 5 divided by what? Square root of 1 minus y squared. So my mission 3 has a dual purpose. There is a sneaky undercurrent of review for the final in mission 3. I don't know if you noticed this or not, but this is part of that larger program of reviewing for the final exam. You had another problem where all of a sudden partial fractions came upon you. Yeah? So you got a chance to review partial fractions a little bit. This one, after we separate variables, we get what? 1 minus y squared dy equal to square root of x squared plus 4x plus 5 dx. We've got to integrate both sides. So many radicals to remove. What technique should we use? You're like, I'm going to use the binomial series with 1/2 power and expand as power series. Said none of you, right? Okay, good. Because we could do it a different way, which would be easier. So how would you suggest we do this? Okay. Did you wait till I was writing to say that? No. All right. So I heard complete the square. X plus 2 squared plus 1, yeah? So what kind of substitution are you going to use on that side? I heard a tangent. I disagree. Not that tangent's not the wrong, tangent's not a, it's not a, here's why I disagree. If you make a tangent substitution, this becomes secant, this becomes secant squared theta d theta, and the net cost to you is an integral of secant cubed theta. And that's where you get stuck? So instead of that, think about this. Cos squared theta minus sinh squared theta is equal to 1. So I should think about x plus 2 equal to, gee, I don't know, sinh theta. See, because if I do that, this is the integral of the square root of, well, sinh squared theta plus 1, right? And then what's my dx? My dx is cos theta d theta. So that gives me integral, this is cos squared, right? So getting to the point, we have the integral of cos squared theta d theta. And then trust me, you can do that integral with much less difficulty than secant cubed. How do you guys want to do the integral? The easiest way is to remember what I've already shown you, which is that it's just like cosine in the sense that there's 1/2, 1 plus the cos of 2 theta. That's true. And so with that identity, you know, this is just 1/2 theta plus 1/2 sinh 2 theta plus a constant. And then you can rewrite theta in terms of x to finish it. Now, if you don't remember that trig, well, the hyperbolic trig identity, how would you do this? You don't, I mean, if you don't remember it, you're not up a creek. I mean, you could still do it. It's not a big deal. The other way to do this integral would just be go, oh, well, I know what cos is. Cos is 1/2 e to the theta plus e to the minus theta, right? So I take that thing, I square it, and that would be the integral of 1/4 e to the 2 theta plus 2 plus e to the minus 2 theta d theta, which you can integrate, right? So if you find yourself integrating a hyperbolic function or some power of a hyperbolic function, sine or sinh or cos, those are straightforward. You just, if you don't remember how to do them at the level of sinh and cos notation, you can go back to exponentials and still do it. It's not a big deal. So anyway, that's that side. Still, you got to solve for x, right? Put the x back in. How about this one? This one you guys are fine on, right? What'd you do? You're like, this is y equals what? Is it sine theta or is it cosine theta? You can go either way. Just mess with you. So, I mean, either way. I like sine theta because then my dx, well, dy here is what? Cosine theta d theta. So we get integral of square root cosine squared theta, cosine theta d theta. And so that's the integral of cosine. Oh, this is cool. Look at that. Almost like I planned it to work that way. Plus cosine 2 theta, right? Probably shouldn't use theta since I'm using theta over there. Let me change I'll swap my theta out for a theta tilde. There you go. And again, you need to solve back in terms of y. But You guys didn't get stuck on this part though, right? Because that's kind of like our first example of trig substitution, right? And to me, this is my fundamental example of an integral where hyperbolic substitution is just better as a technique. Yeah. If I made a hyperbolic substitution over here, what would I do? Well, let's not think of it. I think if I did, I bet if I had a hyperbolic substitution over here, it would end up like an integral of hyperbolic secant cubed. If there's any kind of like duality here, that would be kind of funny if it was that, wasn't it? But that won't help you with the homework. I'm just digressing. Oh, there we go. Now let's party like it's 9710. Some people say more cowbell. I say more top hat. See here. So you guys shouldn't get that reference. Anyway, it's before your time. That's classic SNL? Yeah. Before everything became political. You know, it's very true. I mean, like Seth Meyers' show. Seth Meyers' show used to be like, if I track back, it's the like late, the 12:30 to 1:30 NBC talk show. Once upon a time, that was David Letterman's, back before he got cranky and old. When he used to do fun stuff with audience, like take the audience and like funnel them into a shop, like, or, you know, you get 30 guys dressed up in a bear suit and just put them in a gift shop or something, you know, unannounced, just have them keep filing in, stuff like that. And then Conan O'Brien did any number of inappropriate things in that time slot when he was there. Now Seth Meyers is there, and he does essentially a news show. And I swear, every time I turn into like the second half of it, he's interviewing some Democrat politician. Or it's like, this is such a sort of serious adult show. This is not what's supposed to be here. It's supposed to be adolescent and stupid. It's not supposed to be like about social justice and, you know, whatever. I don't know. I digress. I'm just mostly disappointed. Part of the reason I voted for Trump was I was expecting 4 years of quality comedy. All right, because there is material there, right? You don't need to make stuff up. He has been doing hilarious stuff for like 3 decades in the public eye. If you go back, there is a well-established canon of Trump jokes. Just go back. It pre-exists his candidacy. And yet, for the last 2 years, we have nothing but vitriol from the same people. It's very disappointing. Very disappointing. Very disappointing. I had high hopes for the comedy, the Trump comedy. I may have to rescind my vote for him next time. I don't know. Not living up to my comedic expectations. You guys had other questions? If I keep going, I'm going to have to edit this. Yeah. Mm-hmm. Number 98. Ooh. Hey, this is a good problem. We're supposed to integrate from 0 to 0.5 of sine of 6x to the 6th. To within what? Zero point zero 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 one. Now this is not the problem that's in your homework, because I want you to work that. But this is going to be like that problem, all right? So the idea is very simple. You take the integrand, you replace it with its power series representation, all right? For this one I just wrote up, and for the one in your homework, you can just use substitution of a known Maclaurin series, right? and you'll want to write out the first so many terms. All right, I'm not sure how many. I'm going to go with 4 to start with and see if that's enough. So I'll drop the bounds for a second here and just talk about the integral. So let's find a power series for the antiderivative, if you will. So what is that? That's the integral of x to the 7th times 1 plus u plus 1/2 u squared plus 1 over 6 u cubed plus dot 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 dx, where u equals to what? Where u equals to minus x cubed. All right? So let me simplify that a bit. That's the integral of x to the 7th minus x to the 10th plus 1/2 6 plus 7, 13. This, when I cube the 3rd power, I get the 9th power. 9 plus 7 is 16, so minus 1/6 x to the 16th. I feel confident about that being enough. Now, I've still not integrated, right? I just converted the integrand to a power series, because if we could do that, then we can integrate term by term, right? So that's 1/8 x to the 8th minus 1 over 11 x to the 11th plus 1 over 28 x to the 14th minus 1 over 6 times 17, 102 x to the 17th, I think. All right, plus a constant, right? Fine. So there you go. That's an antiderivative for this integral. So let's put it into practice. The integral from 0 to 0.5 of x to the 7th e to the minus x cubed dx is equal to, well, does the 0 matter? Like when you think about, let me write it this way. Let me call this thing above f of x, big F of x, right? So fundamental theorem of calculus part 2 says that this is f of 0.5 minus f of 0, right? That's what we're doing. What is f of 0 here? It's just 0, right? Because we just ignore the constant. As usual, they cancel. That's 0. What's f of 0.5? Well, it is 1/8 0.5 to the 8th power minus 1 over 11, 0.5 to the 11th power plus 1 over 28, 0.5 to the 14th power minus 1 over 102, 0.5 to the 17th power. Now, the critical observation here is that that is a plus, minus, plus, minus, plus, minus, plus, minus series, right? It's an alternating series. So if we want to approximate the series, we can truncate it at any order that we like, and the error in that truncation is as big, it's no bigger than the next term we've neglected, right? That's the alternating series. So what would happen if we just keep the first term? If we just keep this only, then this is a bound on the error, right? Would that be enough? What's 0.5 to the 11th power divided by 11? Do, 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 do. 0.5 to the 11th power divided by 11. The answer is 0. Okay, I think I didn't let her finish speaking. It's actually 0.00, 4 zeros and then a 4. It's 4 times too big. So this won't work. This won't work because this is actually 0.000, 4 O's and a 4. So that's not enough. We have to do what? We have to keep the first 2 terms for this one. So if we keep this much, this bounds the error, right? And what is that? (0.5 to the 14th power divided by 28. The answer is 0. It just says the answer is 0. It's funny. But it shows me 0.00002. I mean, there's 5 O's and then a 2. So this thing is about 0.1, 2, 3, 4, 5, 2, 2. So this would approximate the integral to within the desired error. It would do better than we want, right? We'd actually be certain of the first 5 digits in that. Now, what is the actual thing? 0.5 to the 8th power divided by 8 minus 0.5 to the 11th power divided by 11. It changed my second 0.5 to 2.5. Oh well, it's not flawless. Yes? Uh-huh. Oh, I don't. I guess. Like I said, I think 4 might be enough. I'm not sure. You know, if I did this and, you know, if I did a problem like this, right? And when I got to this step, I was finding that the terms are alternating, right? But this one's like 0.3, and this one is like, you know, 0.29. And this one is like 0.28 and 0.27. I mean, if they're reducing, but ever so slowly, then I would have to take a different approach, right? I would actually have to find out the formulation for the Maclaurin series as a function of n. And then I would find the nth term in that, and I would set it equal to the error bound and solve for n. But that's not necessary for this sort of problem because I know by its construction that it's just going to be a couple terms, right? If it was a couple hundred terms, then I would need to take an algebraic approach to find the error. But that's not this problem. Yeah. So you don't really know until you get into it. What's the right approach? Oh. If you're doing an integral, it depends on the instructions to the question. So if the instructions to the question say, find the first 3 terms in the power series solution to the integral, then find the first 3 terms. If I say, find the power series solution to the integral, you got to find all the terms. Yeah. Uh-huh.
So the first 3 terms would be just the answer then?
Right. Yeah, this would be this is the value of the integral up to that error.
And the third term,
That's
does it bound that term?
the alternating series estimation theorem says that if we look at the full series, let's call it S minus S2, that's less than 0.00000022 in this case. Where S2 is this. This is S2, the second partial sum. Which my Google voice, I tried, but, you know, Google's not perfect. What can I tell you? Or maybe it's just my speaking. It's probably my fault. We shouldn't blame the Google, the all-wise, benevolent Google, right? Just trust everything with Google. Government having control of broadband, that's a good idea. They would never abuse that. Other questions? 116? Oh, find the integral curve. Now, I won't work that problem, but I'll work a similar one, okay? I guess I work over here. Let me work on the ones that I gave you in the battle. Yeah. So like problem 7 in the battle, right? What was that? Problem 7 in the battle, the bonus battle. It was. I said find the integral curves to f of xy. I had y squared plus 2y plus 1. and x squared plus 3x plus 2. So here was my f. I said find, part A was find the integral curves to this, right? Find integral curves. And remember, we had a discussion. Bless you, yes. We had a discussion where we worked out that the integral curves, so I called this thing P, I called this thing Q, and we derived that the integral curves are solutions to dy dx equals to Q over P. If you've forgotten why that is, I'll just explain briefly. It's because the integral curve has dx dt equals to P. It has dy dt equals to Q. If we're finding it as a function of time, find a parameterization of the integral curve, we'd solve these equations, right? But if that's a parameterization, if that's a description for the calculus of the parameterization, then if we want to find dy dx for that parameterization, remember parametric calculus says you take dy dt and divide by dx dt, but guess what? That's Q over P, so that's why we're solving dy dx equals Q over P, because that gives us dy dx that should be the dy dx we have if P is matching the x velocity and Q is matching the y velocity, which is by definition what an integral curve does, because you know, it's supposed to line up with the curve. That's the idea. Anyway, this is just a kind of sideways way of asking you a separation of variables or that kind of problem, right? So what is this? 3x, oops, I keep doing that. X squared plus 3x plus 2 divided by y squared plus 2y plus 1. And now we're off to the races, right? Like, how do you solve that? Separate variables, right? And the same is true for the problem in your homework that we're just talking about, right? So for problem, I'll say it in words, I won't write it down. But for the problem 116, your Q is what? Q is y, and your P is minus x squared. So you'd be solving, you know, dy dx equals to y over minus x squared. It's actually a little bit easier than this one. Y squared plus 2y plus 1. You got to mind your p's and q's, right? Let's see here. X squared plus 3x plus 2. This expression, mind your p's and q's, this is no longer known by your generation, right? Who's familiar with the expression, mind your p's and q's? You've heard about half participation in this colloquialism. Very good. Yes, sir? I made P on the left. I made P the x component and Q the right component.
Yeah, but can you switch that up? Like,
you could, but then that would be really confusing because I've been using them with that fixed meaning as it relates to setting up the integral curve equation. Like this, whatever goes here is the y component. Whatever goes here is the x component. Is there something in the notes that I've done? It has Q. On the mission, it has Q. And then, what problem are we talking about?
116.
It's negative x squared.
Oh, no. If f equals to, if xy equals to minus x squared y, that makes this P, that makes this Q. You can't separate, yeah. I mean, you're solving. That, you can solve that. You're being a bunch of newbies. Noodles. All right. So let me finish the bonus battle problem, if you don't mind. So this is what, 1/3 y cubed, integrate both sides, right? So 1/3 y cubed plus y squared plus y equals to 1/3 x cubed plus 3/2 x squared plus 2x plus a constant. There you go. That was the solution. That's the implicit solution that describes integral curves or solutions to that. Part B in that bonus battle problem was actually the same question. So part B, I asked you to find the, yeah. 119? Yeah, I can, yeah. This is part A of the bonus battle problem. I just want to point out to you guys, part B of the bonus battle problem was exactly the same problem written in a different way. And in the sense that I said part B was find orthogonal trajectories to what was it? To 2y cubed plus 9y squared plus 2x cubed plus 12x squared plus 30x plus c. Actually gives same. If you work it out, you get dy dx equal to minus y squared plus 2y plus 1 parentheses divided by x squared plus 3x plus 2. So if you take the equation which was given in part B of the bonus battle problem and you implicitly differentiate, you find dy dx equals to this. But then to find the orthogonal trajectories that, you take the negative reciprocal. So to find OTs for that, you get dy dx equals to x squared plus 3x plus 2 divided by y squared plus 2y plus 1. In other words, it's the same problem. Parts A and B were the same problem for different applications to this differential equations. I will be posting a solution to the bonus battle, hopefully later today, if I don't fall asleep. But, I mean, I'm going to try. It's been very good sleeping weather. Hannah, you asked me about problem 119 like 3 minutes ago. So y prime prime plus 3y prime equals 0, making a v equals y prime substitution was the question? Or as I have written, substitution. Not really a substitution, it was a substitution. I apparently can't spell substitution when I wrote this. Y prime prime plus 3y prime equal to 0. I'll say y prime prime minus 4y prime equals to 0, just to make it different. All right?
We did 119 yesterday.
It was an example for 120. Yeah, 'cause we did it today.
Are we good? Oh, okay. So the class says asked and answered. Next, let's see here. So, hey, they said it, I didn't say it. Let's see here. Problem what? 117. 117. All right. So we have Did I remember it right? Or
Is that 117 or is that like 116?
Exactly. Right. Y of 0 equals to 2, was it? Right. All right, so let's work through this one carefully. So first of all, we need to identify here P equals to 3 and Q equals to e to the 3t. Now, I say we need to identify Q as that, but that's not really true. It doesn't matter that you identify Q. What's critical is that you write it in standard form and you do make a correct identification of the P, because P is what we use to form the integrating factor, right? So what did I use for integrating factor in here? I, right? I is exponential of the integral of p, in this case dt, because t is the independent variable. So we've got exponential of the integral of 3 dt. Hopefully we can all do that integral. Exponential of 3t, or if you like, e to the 3t. So that's the first step, is to calculate the integrating factor. Next, we multiply the equation by the integrating factor. So I'm calling the equation in standard form star. And so that gives us e to the 3t dy dt plus 3 e to the 3ty equals to e to the 3t e to the 3t plus 2, which is what? E to the 6t plus 2. Right? And then what? We do the reverse product rule, right? Reverse product rule. In other words, see the product rule in the step above. That's really d dt of y times the integrating factor. You're like, no, it's d dt of the integrating factor times y. Fine, I'll allow it. It doesn't matter. It's multiplication of functions. You could go either way. Anyway, the point is, if you differentiate that product, you get the thing right above, right? Again, this will only work out for us if we calculate the integrating factor correctly. And so that's equal to e to the 6t plus 2. Now we can integrate both sides. Integrate both sides, what do we get? We get e to the 3t times y equals to 1/6 e to the 6t plus 2 plus some constant. Making a u equals 6t plus 2 substitution brings out a 1/6, right? If you don't believe me, differentiate the right-hand side and see if you don't get back to e to the 6t plus 2, right? And then what? Multiply by what? E to the minus 3t, and that gives me y equals 1/6 e to the 3t plus 2 plus c e to the minus 3t. Are we done? I mean, we would be done if we were asked to find the explicit general solution devoid of any other data. You know, if we were not given any other information about the problem, that'd be the answer. All right? But what are we told? Y of 0 is equal to 2, right? So you need to plug that into that to figure out what c should be. Any of you done that? What did you get c for? What did you get c equal to? Did you get 5e squared over, oh no. Oh, it's kind of complicated. Yeah. C is not that pretty. C is whatever you have to add to e to this. C is whatever you have to add to e squared over 6 in order to get 2. Yeah, so 2 minus e to the 6, 2 minus e squared over 6, yeah. That's not wrong. Yeah. So does that suffice for a hint? Maybe we should work another integrating factor method in here. Problem, yeah? Let's look at another one. We probably haven't done quite enough of that in here. But if there's questions, yeah.
Would the C absorb the e to the negative 3t?
Oh, no.
Because the t's in there?
No, okay, so it's fine, it's fine. So e to the minus 3, so let me just show you the details here. I was not writing these things because I ran out of board space over there, you know. So this is 1/6 e to the minus 3t times e to the 6t plus 2. Distribute c, right? So that's 1/6 e to the 3t plus 2 plus c e to the minus 3t. And over here, this, of course, simplifies to, right, y. So that's why y is equal to that. We don't just add c to the answer for a differential equation. Like the way the constant gets wrapped up in the differential equation, it's different for different problems. Because the solution set to a differential equation, it's a family of curves. They typically fill out the plane. But they don't fill out the plane in such a way that they're all related like antiderivatives are, which are just simple vertical shifts, right? Like one of our early examples was the solution set to a differential equation was a family of circles, right? So to get from one circle to another, you don't make a vertical shift. It's something very different. So the way the constant appears in the solution is not just going to be plus a constant very often. It's usually somehow intertwined in the formula. And it's different for every differential equation. For this first order kind of problem, the way the constant appears in the solution can be very different in different problems. How do you know where it goes? Well, you separate variables and you follow the calculus. It puts it where it's supposed to go, is the thing. Yeah. Let me show you guys something. So I don't remember if I actually already posted a I don't remember if I already posted a link to this or not. Did I? I can't remember. Oh, I did? Okay. So you can actually like look at answers to these problems. I mean, what this is looking at is dy dx equals x plus y. This is what the, these are the slopes that that differential equation puts at different points. And then finding a solution is just basically connecting the slopes. So let's see here. So here's a few different solutions. I think I can move this one. Come on. See, what did we look at? Dy dx equals to what? Like, I don't know. How about minus y over x? No, I don't want to zoom in. Go up. Come on. So this one has solutions which are what? See that one constant gives us these two different branches to the hyperbola? And I don't understand. Yeah. Oh, look. Whee! More. It's like all right, that seems unnecessary. Anyway, what happens if we switch that minus to a plus? What happens there? It's going to go from, yeah. So now we've got, well, it's not a circle. It is a, one of these allows me to move it around, but I haven't played with this thing enough. So these are lines. What happens if I flip it, just for fun? What if I do x over y instead? I think we're going to be back to... Now, this is fun, right? Because the way that this kind of software generates things is by what... Do you guys remember... I don't think we ever talked about it here, but there's something called Euler's method, which basically is a numerical method that kind of steps forward bit by bit. And if you jump over an asymptote, you can generate something that's not really a solution. Like there's something special that happens here, and this is sort of jumping over it and creating, that's not real. You know, that's just a computer error. And here's like the one we looked at the other day. You guys got your IDs out? Oh, that's Friday? Okay. See, that is, it's not right, is it? So, you know, part of our goal in calculus is for you guys to get enough familiarity with your surroundings, situational awareness. When a computer does something like this, you know it's garbage, right? So.